any point my PPT is not visible, so kindly.
Yes, sir, I will inform you definitely. So once again, welcome back to all the participants. This is the second session of third day on flow behavior in scour around piers by Dr. Ashish Kumar sir. So let me introduce today's expert. So Dr. Ashish Kumar is BTech with honors in civil engineering from KNIT Sultanpur, Uttar Pradesh. He completed his MTech in 2002 and PhD in civil engineering with specialization in hydraulic engineering from IIT Rurki in 2007. Sir has joined Department of Civil Engineering at JP University in May 2006 as a lecturer in civil engineering. Currently, he is working as a professor and head of civil engineering department. He is the member of various technical societies, including associate member of Institution of Engineers India, life member of India Water Resource Society, IWRS India, ISH Pune, Indian Geotechnical Society, India. He has over 18 years of teaching and research experience in this field. And Dr. Ashish has handled various projects related to sponsored by DST and Himachal Pradesh Council for Science, Technology and Environment. He has guided several students for their master thesis, and currently 3 students are working under him in PhD. He has published a number of research papers in reputed journals, including Journal of Hydraulic Engineering, ASC, Journal of Environmental Engineering, ASC, Renewable Energy, Journal of Hydro Environment Research, Journal of Soil and Sediments. He has reviewed number of research papers in various international journals and conferences. Sir has also involved in the community service by installing the cost-effective biogas digesters in the Himachal Pradesh and nearby area for the last 12 years. So with this introduction, I would like to invite today's speaker, Dr. Ashish Kumar sir, to continue the session and deliver his talk. So welcome you, sir.
Thank you. May I know your good name, please?
Sir, my good name is Sudhanshu Dikshit, Professor Sudhanshu Dikshit.
Okay. Thanks, Professor sir. I am very thankful to the team of Department of Civil Engineering, LD College of Engineering, Ahmedabad. So providing me opportunity in this AICT Training and Learning Academy FDP program. And so thanks to all the coordinators, Professor R.K. Jain, then Professor Sudhanshu Dikshit, and Professor Utkarsh Nigam. And it is my privilege that I have been given opportunity to deliver the expert lecture on the topic that is related to flow behavior in scour around piers. So before I go with my presentation, so let me tell you something about my university so that you may something know about my working area where I am working. So presently I am here in JP University of Information Technology and in the Department of Civil Engineering, and at present I am head of the department. And these are some photographs of my university, and the university campus is basically spread over 25 acres of lush green slopes of the Vatnaghat Hills, which is in the Himachal Pradesh, and it is near to Shimla. And presently, if you move from Chandigarh to Shimla, then it is in between this national highway between Chandigarh to Shimla. And so that is all greeny area, and these are some photographs. So I thought it would be great if I make you all familiar with the JP University. So JP University is basically JP University is basically conceived by a joint vision of Government of Himachal Pradesh and our founder chairman of JP Group Shri Jayaprakash Gaurji in 2000, and in 2002 we start functioning, and in 2003 we start functioning our Department of Civil Engineering, and since then we are running a number of courses in various disciplines of engineering, and also offering MTech courses in the working area. And let us start with the topic, which is the flow behavior in Scava around piers. So let us start with some brief history of the bridges. So why we need the bridges and how it came into the existence. So we all know that since the progress of civilization, it was felt that there is need some structures to cross the waterways. Okay, and in the early civilization, man has to move from one place to another place in order to search their food and shelter, and ultimately he has to cross these waterways, and then the existence of bridges came into the picture. And as we see that bridges are the essential component of the transportation system, either it is the railway transportation or it is the highway transportation. So this structure basically play an important role in the communication of all our human being, either it is communication of human being or it is communication of the goods or material. So that is playing an important role. So these are the some pictures of old bridges over centuries ago, and so just is it visible? Anyone?
Yes, sir. Yes.
Okay, so these are the some
Yes, sir.
pictures which I have taken from internet sources, and first figure you may see that this is the bridge over river Malis, and it is in Turkey, and the year of built is around 850 BCE, and then second is the Tar Steps, and year of built is around 1000 BCE, and its location is in presently inclined. And if we go with the so if we are talking with this Tar Steps bridge, it consists of 7 giant slabs and total of 180 feet long, and are considered the best example of clapper bridge. And according to the local legends, the Tar Steps were built by the devil so he could sub-bath on the stones, and the bridge has been damaged in recent years by flood waters but has been rebuilt. So that is a kind of bridges. And then we have a third, which is the Arcadico Bridge, and the built. This is location is Greece. So these are the some old structures which were built by the early civilizations, and among this, the first one, this, if we talk about this, so this one is the recorded in the Guinness Book of World Record as oldest bridge. Now these are this is the bridges on river Ganga Canal at Rurki, and this photograph was taken by myself while I was doing my PhD work in Department of Civil Engineering, IIT Rurki, and as this was my focus area of research, so I carried this take this picture. So that is the new age constructions while we are creating this bridges on some waterways, and this is the next bridges on river Brahmaputra with double D-shaped bridge pier that is probably taken by my guide, my supervisor, during his visit. Now there is a famous quote: "Man who overlook the water under bridge will find the bridge underwater." So this is very famous. If you are overlooking the water, then ultimately you will find that bridge will be under the water. So this anonymous citation highlights the important effect running water on stability of the bridges, in particular its influence with piers and abutments that is supporting the bridges. So we cannot overlook the power of the water when it is flowing at its full force. Now, piers upon which the superstructure of the bridges rest play an important role in its stability and the safety. And one of the main cause of bridge failure is scour by the flow around its pier and abutment. So what is the requirement? So there is a requirement to calculate the accurate estimation of the scour area and its depth at the bridge sites. And that is basically concern of any hydraulic engineering, hydraulic engineers. And what we see that if we do the underestimation of the scour depth, then what will result? The result will be the shallow foundation, and ultimately we will get an exposure. We will get a chance to failure of the bridge foundation, and that is dangerous for the safety of the bridge. And if we do the overestimation of the scour depth, then it will result an uneconomical design. So somewhere, what is the requirement? The requirement is we have to make or we need some formulation so that we could get the accurate estimation of the scour depth. The one picture which is showing the scouring around the bridge pier. So this is the all scoured area. Now this is the another pictures has been taken in which bridge has been failed due to the flood activity in the river. So these are the some glimpses of the failure of the bridges. Now there is a study which was carried out by Vardhana and Harry Priano in 2003, and they analyzed the failure of 503 bridges in the period of 1889 to 2000 in the USA. And what they observed that the primary cause of failure was found to be flood and scour, followed by the collision from the vehicles. And what they reported that failure of bridges is due to the floods, including the phenomena of scour, is around 52%. Similarly, a recent study has been conducted by Garg, Arcadico et al. Yes.
1 minute, sir. I think it is on slide number 5. So you can make it full screen, sir. Participants, आप लोग की slide change हो रही है?
नहीं सर,
नहीं सर, slide नहीं change हो रही है.
Okay. So it is on the slide number 5. You can make it full screen, sir. I think it.
Okay. Just go with it. Okay. So that is the slide
5 number. Yes.
Okay. So I think there may be some problem. So I am just moving slide in the same manner. Okay. So that you do not get any difficulty. Okay. So,
okay.
Okay, so just wait. Okay, so we were on this slide. So should I move with this slide again? So these are some pictures of old bridges made by the early civilization as they need and they felt the requirement, and some these pictures are taken from the internet sources. So now this is the next bridge on the Ganga canals at the Rurki, and as I told you that is the bridge picture taken by me during my PhD work at IIT Rurki. This is the another photographs of railway bridges. A bridge on river Brahmaputra with double D shaped bridge pier. Okay, and so you can see this is the shape. Okay, so now next let us go with the next. So what I was discussing, that man who overlook the water under bridges will find the bridges underwater. So this is the famous citation and famous quote, and that reflects the importance of the running water on the stability of the bridges. And if we overlook the power of the water, the momentum of the water, and go with the design by overlooking the water phenomena, then probably we will lose our bridge and we will find our bridge under the water. Okay, so that is what we have. Basically, we were discussing about the phenomena of the scouring, which is occurring around the bridge piers, and probably that is playing an important role in the safety and stability of the bridge. So that is one of the main cause of the bridge failure. That is the flow around the piers and the abutment. So accurate estimation of the scour extent and its depth at bridge site is the major concern for any hydraulic engineers. And if we do the calculations for the scour depth, and if it is underestimated, then what will happen? We will having exposed to our foundations during the flood flow phenomena, and ultimately this will be dangerous for the safety of the bridge. Whereas if we do the overestimation of the scour depth, then it will result in the uneconomical design. So these are the some pictures in which you can see that there is a scour, that is the local scour, and or you can say erosion of the bridge pier. And this is the next figure. You can see that in this, we can see that there is a failure of the bridges due to the flood occurring in the river. So these are the few examples how the bridge structure is influenced by the flow of the water. So to study, I have taken here that first study is that made by the Vardhana and Hadipriano in 2003, and they analyze and the failure of the 500 bridges in the period of 1989 to 2000 in USA. And what they observed that one of the primary cause of the failure was due to flood and scour, followed by collision from the vehicles. And they reported that around 52.88% of the failure of bridges occurred due to the flood, including the phenomena of the scouring. Similarly, one study has been carried out in India also, and R.K. Garg et al. Collected information on roads and railway bridges, and they counted for around 2010 bridges, and their source was from the printing media, from the internet, and from the other government officials gadgets. And so they collected the data from 1977 to 2017, and as per their analysis, the failure of bridges due to flooding and scouring was more than 51%. So that was around 51%, might be 52%. So I'm not. So you can refer the you can, if you want to go with the more on this topic, so you can refer these two references. So the concern about safety of bridges scour is primarily due to these reasons that we have still have inadequate knowledge about the scour phenomena, and also we have inadequate data on bridge and abutment square, particularly during the passage of the flood. And lastly, the size of wagons, trucks, and the frequency has significantly increased, and which has increased the load on the bridges. So this is the breakup of the cost of the foundation and the cost of the superstructure of the few bridges. And this is the table here. You can see that some bridges has been taken, and the length of bridges are given here. And this is the cost of the substructure, that is around given in 50 millions of rupees, and this is the cost of superstructure. And thus you can see here almost or more than 50% cost is incurred in the construction part of the substructure. So that shows the need that what sincerity should we have while designing this substructure part of the bridges. And while if you see that mostly when we are designing the superstructure part, we are taking care we are using the different softwares. We are using the finite element methods, we are using the StatPro, we are using some ANSYS software, while when we are going with this substructure part design, we are still facing problem. And in India itself, we are using the LYSIS method. And while if we talk about the USA, and that is the federal FHA, then they are using that HEC 18 circular. So we will discuss that also. So that shows the importance that how this substructure is important part. Now we go with the phenomena of the scouring, and we will then go further with the flow structures around the bridge piers. So here we can see that one of the main cause of bridge failure is scouring of the pier at its supports. And what is that scour is? Scour is local lowering of the stream bed elevation, which takes place in the vicinity. So if you are having a flowing water and this is the flow, and if we place our bridge pier, then what is happening? The erosion is occurring around this structure. So this is basically the local phenomena which is occurring in the vicinity or around the structures, and this is basically generally lowering the bed level. So the scour around the pier is a result of development of this high shear stress due to the three-dimensional flow separation of the boundary layer. Now scour needs to be differentiated from the other terms, degradation. And when we call degradation, so degradation takes place when the transport capacity of the flow for sediment is greater than, okay, so this is greater than transport capacity, greater than the rate which sediment is being supplied from the upstream. So if the supply of the sediment from the upstream is less, and then what will happen? There is a degradation, and there is a degradation of the bed and lowering of the bed level. If this is the bed level, then there will be and this is the depth of flow, then and sediment transportation is coming less in the flow, then what will happen? So it's basically what happens here. So any river has its fixed capacity to carry the sediment. So if it is having less sediment transport, suppose we have created some structures in the upstream of the bridges like dam or some retaining structures which has stopped the water carrying water, and thus stopping its silt, then what will happen in the downstream of the this barrier or this dam or any other retaining structure? What will happen? So what is happening here? The sediment is becoming less at the upstream of this pier. If this is the pier, then what will happen here? So, or suppose there is no weir, there is a normal river as we are discussing, then degradation of this bed level will take place, as every river has its own sediment laden capacity. So it will erode in order to complete its sediment. So that is basically lane balance analogy. So in case of bridges in alluvial rivers, estimation of correct depth of scour below stream bed is important, as it is required in order to find out the overall depth of the foundation. So we have discussed it. So now we come with this, what is the total amount of the scour? So we have divided into it three categories. So first is the local term degradation, that is of the river bed, and then second is the contraction of the scour, and third is the local scour, which takes place in the vicinity of the pier or any other structures. So we will discussing it one by one. So first is what we are having the aggregation and degradation. So what is that aggregation and degradation? So this aggregation or degradation of the stream bed elevation is basically a long-term phenomena, and this changes, as I told you earlier, that is due to the natural or man-induced causes. Suppose you create some structure like dam, okay, then there will be some, as you have made some changes in the river phenomena, then this aggregation or degradation will take place. Now this will affect, or this can affect the reach of the river on which bridge is to be located. Now if we talk about the aggregation, so aggregation involves the deposition of the material eroded from the channel or watershed upstream of the bridges, but is not considered a component of the total score. Okay, so if we go with this degradation, so that is involving the lowering or scouring of the stream bed over relatively long reaches due to a deficit in the sediment supply from the upstream. So that is the important part. So there is a deficit in the sediment supply from the upstream, and it basically contributes to the local scour. Total scour, sorry. So now go with the contraction scour, which is the second part here. So contraction scour is basically lowering of the stream bed across the stream or waterway bed at the bridges. So this what is happening. So this contraction scour result from contraction or constriction of the flow. Suppose you make a suppose this is the river here, and you basically constrict by creating some abutment, so that, and then you create some bridges here. Okay, so while you are creating contraction in the flow, then what will happen? That will result in removal of material from the bed across all and most of the channel width. So this contraction scour is different from long-term degradation. In that, contraction scour occurs in the vicinity of the constriction or bridges, maybe cyclic or related to the passage of the flow. So whenever there is a construction of the river bed, river width, so then this phenomena occurs. And then this is the third, which is the local scour, and this is basically occurring or removal of the material around the piers or abutment, spurs or abutment, and it is caused by an acceleration of the flow and resulting vortices induced by obstruction of the flow. Now when we talk about this phenomena of the local scour or contraction square, then two phenomena basically occurs. The flow may be the clear water, or flow may be the under live bed condition. So when we call it as a clear water scour or live bed scour, so what is happening here? There is a phenomena that in the clear water scour. So what are the condition here? If the shear stress on the bed upstream of the structure is less than the shear stress required for the initiation of the sediment particle. So what does it mean? Suppose this is the river here, this is the water depth, and we have some, this is the bed of the river, it is having some sediment which is having a size D50. So basically we find out with this D50 what is the critical shear stress, tau c, with the with shield criteria. Okay, so that is the critical shear stress. Okay, so this critical shear stress is required. So, and there is a flow here which is having itself shear stress. So this tau is the shear stress of the flow. So when the shear stress of the flow tau is less than the critical shear stress, then what will happen? There will be no movement of the sediment particles from the bed surface. Okay, and this is the condition when there will be a clear water phenomena. Okay, so in this case, if we are if we are having some bridge pier or bridge structure which is having this bridge, then what will happen? The scouring will take place by lowering of this bed level, and there is no input in this Scava hole, which is the local scouring. Due to this, as there is a clear water, there is no sediment transport here. So final equilibrium is reached when transport of sediment out of this scour hole. So this is the scour hole here which is created. This is the depth of scour here. Just wait. This is the depth of scour denoted by letter ds. So this is what we have. Okay. So it takes a long time for such a condition to reach. Now go with the second criteria. So
sir,
now,
sir,
okay.
Sir, I have one question.
Yeah.
Sir, always we take D50 size particles
Yeah.
while considering the shear.
When we are calculating the critical shear stress, then we consider in the SIL criteria we have the D50.
Okay, sir.
Okay, so these are the some typical clear water scar situations, and that is what we have. First, we have bad, which is having a coarse bad material streams. Second, the flat gradient of the stream during the low flow. So that is also depending upon how much slope of the bed you are having. Then the local deposits of the larger bed materials that are larger than the biggest fractions being transported by the flow. So and last, which is important, that is the armored stream beds. Okay, so armored stream bed where the only locations there tractive forces are adequate to penetrate the armor layer. Normally armoring of the layers is what something there is a deposition of this larger particle size, and below that what we are having the small particles. So in that case also there will be no transport of the bad material to the stream. And also that is fifth, vegetated channels or the flood plain over banks where velocity is very less. Then we go with this live bed Scava, and here what is the criteria? The shear stress of the flow is greater than the critical shear stress. That means this tau of the flow, which is denoted by tau naught, will be more than the tau c. Okay, so this live bed occurs when there is a transport of the bad material from the upstream reach into the crossing. Okay, so this live bed scour is basically cyclic in nature. That is, the scour hole develops during the rising stage of the flood, refills during the falling stage. So if you are having a flood situation, and suppose just wait here. So in case of what is happening here, suppose this is the scour, which is this is the river bed. Okay, now what is happening here? When there is a flood, then what will happen? The flow increases, the velocity increases, the shear stress increases, and ultimately what is happening? There is a development of the scour hole. When flow recedes, when the flood recedes, when the flood goes down, then slowly the flow depth decreases, and ultimately what happens? This slow down or falling stage refills this scour hole. So that's why what is happening here, this live bed scour is basically is a cyclic in nature, and when we compared it with the clear water scour, this type of scour occurs more rapidly and oscillate non-periodically. So here, this is basically the diagram which we have taken here. So here what is happening, this side we are having the scour depth that we may donate by the ds, and this is the time. So here you can see that in case of the clear water scour, okay, so what is here, what is happening? So it takes place in a long period of time here. Okay, and if we talk about this live bed scour, so this is the live bed scour, and In this case, the Scava depth increase sharply when we compare it with the clear water Scava. And then, as I told you, there is a fluctuation and there is a oscillations as the Scava hole is filling and refilling again and again. So here the difference is this is the average of this is taken as the equilibrium Scava depth, while the maximum Scava depth is reached in case of the clear water Scava. Okay, so there is a difference of 10% here. So in general practice, the maximum depth of Scava is approximately 10% greater than the equilibrium Scava. Now we go with the mechanism of this Scava. Basically, what is happening when a flow is approaching towards the pier. So here in this figure, this is a typical figure taken from Melvin and Rurki, 1991. And here you can see that there is a Scava hole which is created. This is the sediment bed, and this is the pier which is founded in the river. So what is happening here? So when is pier is placed in a stream, and it is in such a way that its axis is perpendicular to the flow. So this is basically the axis. This is axis is perpendicular or normal to the flow. So what is happening here? So as flow is approaching towards the pier, what is happening at the face of this pier? So what is happening? The flow becomes, the velocity becomes 0. And due to this, what is happening here? Due to this, there is a stagnation pressure in front of the pier, and due to which what is happening, the water surface is increased. So this is increased here, and this is a result while we are getting this surface roller. So basically surface roller is formed. Also, it is creating an adverse pressure gradient in the longitudinal direction, and also at the same time, it is creating a favorable pressure gradient in the downward direction. So you can see that there is a downward direction of the flow here, and then there is a formation of this vortex. You can see here there is a formation of vortex. So what is happening here? This downflow rolls up again, and it continue to create the Scava hole by interacting with the incoming flow. So this flow is coming here, then the downflow is again interacting this incoming flow, and then ultimately it is creating a vortex system, and this is called as the horseshoe vortex of the pier, and it is extending past to it. So this horseshoe vortex carries out the transport of the eroded material away from the pier. So as the Scava depth increases, the strength of this vortex diminishes, and thus there is a reduction in the Scava rate. And also this is the downstream of the pier, and here you can see that at the downstream face of the pier there is a system of the wake vortices. So this is the system of wake vortices which is formed by rolling up of the shear layers generated at the surface of the pier. So both this horseshoe vortex and the wake vortices erode the sediment from the base region around the pier, and that is as we go away from this Scava hole again, so then at this area the turbulence becomes less, and ultimately we get the deposition at that area. So these elements in the flow individually or in combination result in the local Scava around the pier. Just wait. So this is another three-dimensional picture. So how the horseshoe vortex is creating here, and how this is propagating in the downward side, thus increasing the Scava hole, and on the upper surface you see the this is the formation of the formation of what is this formation? If anyone tell? On the downstream side, On the downstream side, this is the formation of wake vortices. Okay. And on the upstream side, you can see that there is a formation of the horseshoe vortex. So this is the basic here. So there are a number of factors upon which the magnitude of this local Scava depth at piers and abutments depends. So there are a number of factors, and if we talk that in terms of the flow characteristics, you can see we have the flow characteristics, we may have sediment characteristics, and also we may have pier characteristics. Okay, we may have different types of pier shapes along the which may vary along the length also. We may have different type of sediment, we may have different flow characteristics. So here we have given number of the factors here. So that is the velocity of the approach flow, then depth of the flow, what are the discharge conditions here, what is the angle of attack of the approach flow. So suppose this is the circular pier and this is the flow condition. So now in case this is the circular pier, then there is no problem because this is a symmetrical. But if we are having just wait, this double D shape structure here, then what will happen here? This is the in this angle of attack is 0. But in the due course of the time, due to the meandering process, river may change its direction, and then the flow of direction may be like this. So this is the basically angle of attack is changing. So there are factors like this when we get change in the depth of the Scava. Then what is the shape of the pier and the abutment? What is the bed configuration? What is the size of different bed materials, size and gradations? Then there is some obstructions like ice formations, jams of debris. So these are various factors, and I am not going to discuss all these factors because it is a different part to discuss how the Scava depth is affecting due to all these factors. So here just this depth of Scava we have divided. We have shown here that it is a function of pier geometry, then sediment characteristics, then flow characteristics, and the fluid characteristics. So as here we have written that fluid characteristics do not change much from one situation to the another situation. If we talk about the viscosity of the flow, okay, for example.
Excuse me, sir. How the angle of attack will be 0, sir? It will be in proportion to the flow line, na, sir, gradient.
Yeah. In case of the circular pier, from all the direction you are getting the uniform structure. But in case if this is the D-shaped curve or any other structure, then in case the angle of attack is now changed. This is basically changing. Okay. So this is basically angle of attack that may be 30 degree, or river may go after some time, river may flow like this. So in this case, the Scava flow pattern will change drastically.
Okay. Thank you, sir.
Sir, hello. Sir, hello. Sir, you said that the depth of score depends upon the geometry of pier. So, which shape of pier makes least depth of score?
Pardon. What did you say? Your voice.
The shape. What is the shape of pier that makes least score depth?
Which least?
More resistive, sir. Against the scoring, more resistive against
that has least score depth.
Yeah, normally we are working with in Indian subcontinent. What is the basic nature is we are basically using the circular uniform piers. Okay, circular uniform pier. So basically it is having an advantage if you are working, if the direction of flow changes at any part, then there is no further changes. Okay, so normally what we go with this, and all the references is made with respect to this.
Yes, sir. Okay.
Okay, so study related to the Okay, so study now are related to the local Scava around the bridge pier. So here we can see that area has been extensively researched by a number of researchers, and as such, extensive review of literature is available. Extensive work is on this. It indicates that there are a number of equations in order to find out the Scava depth around the bridge piers, and some of them is classified into different categories. So what we are having this. So in the earlier that work is started, and this is the Larsen and Toch, who was the first probably to work on the flow field and the estimation of the Scava depth around the bridge pier. So, so he basically started this work, and how, and just at that time you can see that we don't have so much of laboratory facilities like today we are having latest instruments. And he just used simple gauge in order to find out the Scava depth. But as the time passed away, now we are having the latest instrument like acoustic Doppler velocimeter, and prior that we were having the film wire anemometer, and so on. There are various things to find out the depth. So this is basically the probably the first one to work on find out the depth of the Scava. So various equations after that was given by the various researchers, and basic concept was in terms of depth of Scava divided by the depth of flow. Okay, and this B is the width of the pier. So here we have written here. So I'm not going to explain this. So this is all the laboratory experiments done by the various researchers. And this is the type 2 where the Scava depth equations have this form in the form of the fluid number, and fluid number, all you know that is by U by under root GH. So some researchers have done work on this. And this is the type 3. Here you can see that again some equations has been summarized in this form. So where we have taken the fluid number and the Reynolds number of the flow. And also we are having this. So now coming to this part. So after that a lot of research has been carried out on the estimation of the Scava depth using the different sediment, either it is also in the live wet condition or in sediment or in the clear water conditions. And also some work has been carried out in order to find out the time variation of the Scava depth, how Scava depth increases with the time. Okay, so here I have named some researchers starting from Chabert with 1956, then Melville, Atma, Yanmach, Kothari, Olivito. And this is myself, the work has been done with my supervisor Kothari and Kumar. So a number of literature you can find in this field. Now I am only discussing here two equations, and one of that is the equation which is used to get the pier Scava in USA, and this is heavily influenced by the Federal Highway Administration. So I am only discussing only one part of that. It is a complete manual, and any one from you, if you are interested to work in this field, can freely download this HEC 18 circular. So kindly type in the Google and you will get this freely download. Okay, so kindly go through that if you want to work on this area. So this is HEC 18 pier Scava equation. So this is the basic equation which is having the coefficient K1, K2, K3, that is taking into account the shape of the pier, then angle of attack, and the bad conditions. Okay, then this B is the pier width, and H is the depth of flow, and this FR is the fluid number. Okay, so these are all the criteria which is given here, and these are the basically conditions here. What are the common pier shapes which has been given in HEC circular 18, that is here you can say this, you may write here, this is written here as A, you please may convert it as B. Okay, this is all B. Okay, so these are the different shapes, and this is the correction factor table, and that has been retrieved from HEC circular for your reference, for your guidance. So here you can see that these are the student was discussing about in which pear shape we are getting the less scouring. So here you can see that this round nose as this round nose or this circular pear is having the K1 factor as 0.1, and while this sharp nose is having a factor of 0.9. So probably and definitely as per the HEC, if we are using this sharp nose shape pear, we are getting the less Scava. Then this is the angle of attack, and this is the angle of attack. This is 0 degree, 50 degree, 30, 45, and 90 degree. And this is the correction factor K2, which you can apply as per the angle of attack. And last table is this for the factor K3. And this is given as per the bad condition. This is clear water, then plain bad. Then if you're having small dunes, medium dunes with a height given of the dunes and fit. Okay, so you can put all the details from this table in order to find out the pear Scava. Now, next we go with the commonly used factors in India, and in India we basically find the design depth of Scava as per the procedure explained in the IRC code 78 and IRC 5. And for the natural channels flowing in the alluvial, the mean depth of Scava below flood level can be calculating uses the Ldce's formula. So this is the reference which I have given. You can see that for more references. That is the standard specification and code of practice for roads and bridges. Okay, so what this basically says equation. So this is the design discharge for the foundation design, and this I have taken from the code IRC code 78/2014, and as per the catchment area we can increase the over design discharge in the percentage. Okay, now just I think some data is up and down. Just wait. Okay, just go down. This slide is mismatching. Okay, and just wait here. Okay. Okay. So this is the formula by which we can find out the mean Scava depth below the HFL for the natural channels flowing over the scourable bed. So this is the formula by which we can find out, where Q is the design discharge per meter width of the effective waterway, and F is the Ldce's sill factor, and all of you know this equation, these two equations very well. And maximum depth of Scava will be 2 times of this dLQ. Okay, and this is the type of material which is referred in the code, and this is the sediment size, and the code has provided directly the value of F you can use, and that is varying from coarse sill to the heavy sand. And it is also given in no rational formula or data for determining the Scava depth for bad material consisting of gravel and boulders. So now coming to the part with the flow around the circular bridge piers. So now this flow field, the process of Scava around bridge pier, as you have seen earlier, that this is basically a complex 3-dimensional flow distribution and the sediment transport around the pier. So now what is, there is a complexity in this. there is a flow, three-dimensional flow distribution as the water reaches to the or close to the pier. Okay, so you have seen what is the mechanism of the Scava, and if we take here the flow pattern within the Scava hole around the circular uniform ridge piers had been studied by various researchers, including Melville and Rurki, then Ray et al., Ahmed and Rajaratnam, then Graf and Stiato, D. Riker, then by ourselves also. This is Kumar and Kotiari, and then all others. So the phenomena of this, how to get the flow field, how to understand that flow field around the pier, that has been studied by several researchers. So now in the coming slides, we are going to discuss how we can get this flow field. So why there is a requirement? So a detailed understanding of this flow field modified due to the presence of this pier is essential to model the phenomena of the Scava. So as I told you that we have a number of studies has been carried out, and relatively if you talk about the compound bridge piers, which we'll be discussing in the next coming slides, so very few studies has been carried out. So today we will be discussing this also. So first go with the phenomena of the turbulence here. So all you know that what is that turbulence? Turbulence is basically depending upon whether your flow is laminar or laboratory, and if your flow velocity is very less and such that your Reynolds, basically that is depending whether flow is laminar or turbulent in the open channel flow. That is depending upon the criteria of the Reynolds flow, Reynolds number. Can anyone tell what is the criteria for this laminar and turbulent flow in the open channel? What should be the Reynolds number, if anyone?
Sir, less than 500 for laminar and more than 2000 for turbulent.
Good. So normally, if you are having very less velocity, so if you are working with this Reynolds number, that is the rho d v velocity and mu velocity v over nu, where nu is the kinematic viscosity, and this d is basically taken as the characteristic length. Okay, and in this case, when we are working with the open channel flow, you can take as a depth of flow, and v is the velocity here. So if the velocity of flow is very less in occurs. So normally what is happening in basically in the open channel flow, we are having the turbulent flow, and this turbulence becomes more prominent or more dominant when a obstruction is encountered or obstruction is placed in the flow. Okay, so suppose if you are having this river is flowing and there is no obstructions, although you are having a turbulent flow as Reynolds number is more than 500, but turbulence intensity will not be high. Okay, but if you place some obstruction within the bridge pier, then what will happen? The turbulence basically increases surrounding this obstruction. So here turbulence increases in the surrounding area. So here we are going to discuss how this turbulence is getting prominent and in what area the turbulence is reducing and how turbulence is increasing. So here you can see that this is some vortex is here given, which is showing that turbulence is going on here. Some vortex formation is going here. Okay, and this is the die traces, and this area is having some turbulence here. So this is the motion of the flow. This is the motion of the die. Okay, so let us discuss some more about this. Now, how you can characterize this turbulence. So in the earlier presentations, you all might have gone all these things. So I will not discuss much more, but at the same time, I would like to briefly tell you that what is that turbulent eddies. So normally if there is a flux, there is some obstructions in the flow, then what will happen here? So if you are having some instrument which can capture the instantaneous velocity, okay, with reference to time, as you can see that. So like acoustic Doppler velocity meter. Okay, so in that case, what you can get with the help of this acoustic Doppler velocity meter, you can find the instantaneous velocity in the 3 domain. So here I have written only u and v. You can also find u, v, and w component of the velocity, and all these component you can record while you vary the time. So now you can see that as there is a fluctuation in flow is not flow is under turbulence condition. So what will happen? You can see there are some spikes here you are getting. So these are some spikes. Okay, and at each and every point you are getting the velocities. Okay, and these velocities, if you catch here at each point, the velocity is defined. For example, you take, suppose you are capturing the velocity at this point, the velocity will be ut. Okay, so if you average down all these velocities, if you make average of all this velocity, then what you are getting? You are getting the u mean, okay, or v mean or w mean. Okay, and with this u mean, which is the u mean, the difference at any instant of the velocity ut will be or is treated as the u prime or v prime or w prime. So these are the basically fluctuations here, and more is the turbulence, more variations you will get here, more magnitude of this u prime, v prime, or w prime you will get here. So that is what and how you can calculate. So mean velocities, so we have defined only in the terms of u. You can similarly find out for v and for w component also. So you are getting in 3-dimensional u, v, and w. Okay, perpendicular. So that is what you can find out the mean velocity and turbulence fluctuations. And the third is the turbulence strength. So density of the any turbulence can be find out using this RMS. Okay, so that is what you are having, u prime into u prime. Okay, so I will be showing to you all these data which we capture with the help of instrument. So these are the all turbulent characteristics by which we define the turbulence intensity. That is all in the u direction, that is in v direction, and that is in w direction. And these are all the Reynolds stresses. So we will be discussing these. So now we just carried out some experiments in order to understand the flow behavior around the or flow field around the pier in the laboratory. So this is the laboratory flume at Department of Civil Engineering, IIT Rurki. So where the experiments were carried out during my PhD work. And this is the next figure. You can see while flow is running here, and just so this flume was basically 30 meter in length, and that was 1 meter wide, and the depth of the flume was 0.6 meter, and the flow was adjusted here. This is the basically inflow of the water from here, and there was a honeycomb structure here, there was the straightener here, so that the turbulence of the flow while it is coming here in this area get dampened down. Okay, and you are getting the more or less flow at a or flow without turbulence. Okay, so now this is the definition diagram. So here in the experiments, basically what we did here, we used two types of pier geometries. One pier geometry which was having the uniform pier width, that is the B, across the length. Okay, if this is the bed, if this is the flow depth H, and in the second case we use the compound piers. So this is basically defined as the compound piers, and you can see that this is basically the well foundation here. okay, or vacation here, and over which we have the pier. So these two types of geometries were used to get the flow, how the flow alters due to this obstructions in the flow, that is due to this pier. Okay, so here you can define this is the B, which is the width of the pier, and this is the width of the foundation. And here you can see that this top of the footing, okay, this is the foundation or top of the footing, this is showing this is below of the bed. So we have taken three conditions here. So we have treated Y as negative when top of the foundation is above the river bed. Okay, so we have used just four conditions here. So these are the experimental details which we have taken, and so here we will be focusing on these four experiments only. Okay, so these are the conditions which is work on the rigid bed conditions when we did not allow the scour hole to develop, and we basically made rigid our bed, and then we find out how the flow structure is there around the bridge pier. Okay, so that first two is basically we are not going to here discuss. So if anyone is needed, then he can contact me, then I will share with you all these details after this. Okay, so this first two we are not going to discuss, and these four experiments now we are going to discuss how flow is altering how flow structure is altering here. So this is the first when we are using the uniform pier. This is the non-uniform pier, and these are the three conditions here when we are putting. So just explaining here what we are doing here. So here you can see that the first condition is the uniform pier. In the second condition, what we did, we just wait. This is our just wait. Okay, so this is our foundation. Okay, so this is what condition, this is the top of the footing which is matching with the river bed. Okay, this is the depth of flow here. So this is the condition Y is equal to 0. In the second condition, what may happen, we have tried to keep our instrument our footing. So if this is the now second condition, how we can define, now this is the river bed, and this is the third condition, rather this condition. Okay, so this is the plus B star by 10. So here we have down our value of Y. So this is the river bed here, and we try to find out the flow characteristics in the river in this scour hole. Okay, and in the third condition, what we did, this is the, and this we are going to now discuss this. So this is Y is basically in this condition, this B star by 10, or here B star is what? B star is this. In our experiment, we use this 210 mm. Okay, B star, and this B as 140 mm. Okay, now in this condition, in this now we will discuss this now. Now in this, what we did, we exposed our foundation like this. Okay, now this Y becomes negative here, or this is the bed level. Okay, so these three conditions of the non-uniform pier and this one condition of uniform pier scour hole has been discussed in the coming slides. Okay, so so this is the scour hole which is developed around the uniform pier, and this has been cemented. So after draining out the water, what we did here, so we have to carry out the flow characteristics around this scour hole, around this area. So what we basically did, we basically drain out the water, then we simply sparkle the light solution of the cement in the scour hole area and in the surroundings, so that further scour hole do not develop here. So this is the scour hole geometry which was developed during a period of the when flow was run for a period of 7 hours, and in this 7 hours we developed the semi-equilibrium scour hole. Okay. Now this is the instrument which we used to find out the three-dimensional velocity component. I think all of you have gone through this acoustic Doppler velocimeter characteristics. Have you gone or not? I think that is not need to explain now. Anyone? Please, anyone?
It has been explained, sir, already.
Okay, so I think there is no need to explain. So in this experiment also we have used this acoustic Doppler meter, and we use two props. One is the down looking and another is the up looking prop. Okay, so this is the basically measurement stations we used in order to get the flow structure. So here you can see that this is the direction of flow, and this is basically the plan, and this is the pier here you're having. This is the plane, vertical plane. So here you can see that in order to get the flow structure around the uniform pier, as this is this case, so we have taken 7 planes, 4, 5, 6, 7 up to 180 degree at an interval of 30 degree, and this part will be similar, so that was left, and in each vertical plane we have taken the vertical distribution of the velocity, okay, for the overall depth of the flow. So I will explain you for a particular plane. So for example, these are the distance. You can see that this is 100 millimeter to up to 400 millimeter. So what we did, we take the vertical distribution of the velocity over all these node points, which is covering the Scava hole and also covering some extent of the Scava hole. Okay, so now just wait here. I will show you that. So just wait here. So now suppose let this is the pier structure here we are having, and this is the river bed or channel bed here, and this is the Scava hole. Okay, and this is the going up. So if this is the direction of the flow and this is the 0 degree angle, then what we did, we have taken the vertical profiles here. So if this is the depth of the flow, then what I did, we have taken the vertical distribution of the velocity. So just go with this. So we have taken different vertical. So this is the second. So we have divided the entire flow area into number of the cross sections. Okay, so this is at a distance. If you take this is the center, then this is at a distance of 100, then this is at a distance of 140, then this is at a distance of 170, and we go up to 400 millimeter, okay, or 40 centimeter. Okay, so we try to cover all the Scava hole, and in all these, what we did, these are all vertical profiles. So we at a distance, just we took first measurement at a minimum distance from the bed, 4 millimeter. Then at a vertical distance of 1 centimeter, we took the velocity measurements component UVW. So that was taken at all the levels here. So what we did, we used down looking probe here, and we just getting the values. We systematically increased up our probe with the help of the instrument, which you will see in the next figure. So this is basically the setup which was created in order to get the flow field around the Scava hole, and this is basically we have taken a compound pier here. So this is the foundation here, and this is the pier. Okay, this is the foundation, this is the top. Okay, so this is the acoustic Doppler velocity meter, and this was the arrangement here by which we could make down our instrument down to the Scava hole and up to the Scava hole. Okay, and this is how. So we just move down and down the this instrument acoustic Doppler meter, then we move this area, this area, this area, and this area. So here we could read the distance in the x-axis. Okay, so if you consider this x-axis, so this is x-axis, so this is y-axis, and perpendicular to that is the z-axis, where you can get the flow component. So here you will see some small video how we capture the data. Okay, so just wait here. Just wait. It could not complete. I am running again it. So here you can see that we are capturing the velocity fluctuations within the Scava area. And that data is basically recorded with the software provided by the Nortec ADV, and here you can see that we are recording the continuous data here with this SNR range. So here you can see that we can record all these. Just wait, it is creating again problem. So just see the video. Okay, so that you can see that data is recorded in the software, then this is processed. Okay, so this is the illustration of the measured velocity component. You can see that all these three components are recorded in the x direction, y direction, and z direction. Okay, so here you can see that the velocity is here 29, then vy, and then this is vz. And we are again having some signal to noise ratio and that correlation ratios. So readings were taken around all the vertical planes, 7 different verticals plane. And this you can see, this is an electronic bed level recorder, which record the depth of Scava. And here you can see that this is the photographic view of this bed level recorder from the Netherlands while taking the measurement of the Scava depth at a upstream nose of the circular compound bridge pier. So this is the another video. Just wait here. I am trying to run this. So this is the gauge by which we have measured the depth of flow. This is the end of the flow.
Excuse me, sir. Excuse me, Ashish, sir.
Hello.
Sir, how many instruments have you have used there?
A total number of 6 experiments were conducted around the 6 different pier geometries. Okay, so you can see here.
Sir, actually, I want to know the name of all the instruments you have used.
Oh, this is the acoustic Doppler velocity meter. First, I used to find out the velocity fluctuations and velocity measurements. And second is the bed level recorder, which records the Scava depth. Okay. So 2 instruments.
Okay, sir.
Okay, so just here you can see that. So we were discussing about the 4 experiments. I'll just wait here. So here you can see that these are the basically contours which were drawn with the help of data collected around the Scava hole, and these were the contours created for the. This is for the uniform pier, and this is the pier here you are having. This is the condition when we are having y is equal to 0, and this is the Scava geometry when we are having y negative. That is means above the footing is above the bed level, and this is what we have when we are having footing below the bed level. So you can see that the extent of Scava hole is now here less in comparison to the even when we are having the uniform Scava hole. So when footing is basically if this is the bed level, So if footing is below the bed level, then the extent of scour hole get reduced as and if this is the water level here, then what is happening? So some extent of this vortex is resting on this area also, and thereby reducing the strength of the vortex. So that we will discuss more in the next lecture on next day here on 9th. Okay. So here, this is the geometrical configuration of the scour hole around the compound bridge footing and that work. So this has been created and with the help of the software surfer. So that is showing the scour hole here, and here is the deposition on the downstream part. This is the direction of the flow. Now just discussing the results what we got in this. Just can you wait for a while and just wait for a while. Okay, just hold for a while. Just wait for a while. Okay, just give me 1 minute. Just wait, just wait. Okay, so this is the normalized profile of the velocity component uv and w, which is measured on the upstream of the pier. Okay, so now you can see that here r is the radial distance, and this is basically taken at the plane alpha is equal to 0 degree. That is just upstream of the pier. So these are the three different graphs here. You can see. So with the first graph, as you can see that here, first understand what we are doing here. This is the u by u infinitive, where u infinitive is the approach flow velocity, which is in this case is 20 centimeter, 28 centimeter per second. Okay, and depth of flow here is h, which is 16 centimeter. And this z is basically the variation of the depth. So here this 0 represents the bed level. So this is the bed level here. Okay. So this is the condition above the bed level, and this is the condition below the bed level. First thing is this. So please understand this. And this u is the velocity at any average velocity at any point. And this is basically normalized with this approach flow velocity. And this h is normalized. This z, which is the variation of the depth while we are working in the scour hole or within the area. So just wait here. Just I try to show you. Just wait. This. So this is basically z. Okay. and this is the total depth h. So what we have done, we have normalized this z by h, and this level is considered as z, that is 0 level. Okay, so below this we have different, and below this is the different. So here you can see in this figure, so this is above, this is, it is taken as positive. Just wait, just my so this is here positive, and this is below is the negative. Okay, z by h is negative. Okay, now if you see the first figure, so here you can see that some data is lying with this negative value. U by U infinity is negative value. Okay, so this is all negative value within the Scava hole. Okay, because this is below the bed, so this is all is the Scava hole area. While above the Scava hole, you can see that these all values are positive. So in the plane, what is happening here? Here value is R 100, then it is increasing in the size with this symbols. So this is just close to the pier. This value is just close to the pier, and here you can see that when it is close to the pier, the velocities get reduced, and also within the Scava hole we are getting the negative U component. This negative U component means there is a reversal of the flow. Means what is happening here? This is in the Scava hole. So this is the U component of the velocity. There is a reversal of the component velocity. So velocity is getting reversed. So that is why we are getting the negative component of the velocity. And this maximum negative value of U, which we observed, that was around 0.36 times of the this approach flow velocity. If you go with this V component, so in this V component, what we see, there is this there is a negligibly small fluctuations here, and we have V velocity is very less when we compare with the U component of the velocity. Now there is an interesting thing when you go with this, the W component. W component is this, okay, velocity. So this is the graph, which is the graph showing close to the here. So here we are having this positive value, which is indicating that this W component is in the upward direction. So flow is in the upward direction, while this is showing that flow is in the downward direction. This is showing that flow is in the downward direction. So here also we can see that it means that there is a dominancy of the downward flow. Flow is coming into the downward direction, then this is coming into upward direction. So what is happening in this hole? So close to the, this is the downward flow which is happening here, and close to the bed, the flow direction is in the upward direction. Similarly for this area also. Okay. Now these are the results for the normalized profile at the 90-degree plane. So in this case also you can see that approaching to the pier. So here also you can see that this is the distance all we have taken. So approaching to the pier and below the general bed level of the U component showing the decreasing positive value. So as we are moving away from the pier, so this is the 400, and this is towards the when values which are away from the pier. So as we are going away from the pier, what is happening? So U component is decreasing here. Also, if you go with the V component here, so here in the V component also we are showing that at the 90-degree plane you can see that these values are positive within the Scava hole. That means there is a component of the velocity. This is the pier. and this is the flow. So this is taken at this 90-degree confluence. Okay, so close to the pier, we are having this component. Okay, so here as you are moving away from the pier, the v component is increasing. So that means this is the u component here of the velocity, and this is the v component. Okay, so as you are moving away from the pier, the v component of the velocity is increasing within the Scava hole area. And this is the w component here. You can also see that these are the, again we are getting this values, and this indicates that there is a upward motion of the flow. However, its intensity is less or magnitude is less when we compare with the 0-degree plane. Just wait. Hello. Now, this is the normalized profiles here in the plane alpha is equal to 180 degree, which is on the downstream of the pier. So here we see the different trend here. So that is just different from the what we observed at the upstream of the pier. So here you can see that all values are lying in this range, W by U positive. Okay. So here what we are having, there is a W component is dominant. In the plane alpha is equal to 180 degree, what we are observing, the U component shows a reversal of flow. So this is basically reversal of flow. So as you are moving in the upward direction, so near the water surface, we are observing this reversal of flow here. So U component is basically larger as compared to its value near the pier, but it still has a decreasing tendency near the water surface. So here you can see that here within the Scava hole, we have the velocity which is having higher magnitude, while we are going above the Scava hole, the magnitude of the U component of the velocity is decreasing. Similarly, if you go with this V component of the velocity, so in this V component of the velocity, what is happening here? The normalized value of V component is seen to vary between this segment. Okay. Now, as we were discussing this in this plane of 180 degree, what is happening here? There is a upward flow in the downstream region. So all values of W are the positive. So that means there is a upward flow of the W component. Okay. So similar observations were also noticed by the graph and STR2 at this plane, and just behind the plane, just behind the pier. So this is basically denoting just behind the pier, and just behind the pier, what we are observing that this value is 0.72 times of approach flow velocity, and same is positive, and hence it is in the upward direction. So these are the some characteristics values here, and here these figures shows the normalized profiles of the component of the turbulent intensity and the Reynolds stress. Okay, so here this is for the plane of alpha is equal to 0 degree, and you can see that here that this is the turbulent intensity for the U component of the velocity. This is V, and this is for the W component of the velocity. So here within the Scava hole, you can see there is a turbulence here, and the magnitude is also showing that how it is intensify here, how fluctuations is here, while these are the Reynolds stresses here. So this is within this Scava hole region. So this is showing that we do not find any trend here. Just if you go with this, similarly, this is for the 90 degree, and this is what we are having the trend of the turbulent intensity for the plane of 180 degree. So here you can see that. So here you can see that this is having a scale of 1 to 12. You just note here, while if we were dealing with this was having a scale of 1:8, and here you can see that the turbulence in the wake region, or this is in the at the 180-degree plane or in the downstream plane, the turbulence is more when we compare it with the upstream region or at the 90-degree plane here. So these all you can see that these are not showing any conclusive trend. So the flow in the downstream side. So if this is the downstream side, okay, so if this is the downstream side here, and this is that, so in this region, in this downstream side, flow is more turbulent when we compare it the upstream plane. So this is the normalized profile of the turbulent kinetic energy here. So basically so combined effect of this turbulent combined effect of all these three components of the turbulent intensities can be defined with this turbulent kinetic energy. So basically we define this K as U prime, V prime, and W prime. So combined effect of this all turbulence can be shown by the K, and here you can see that this is normalized again by the U star, where U star is the shear velocity of the flow. Okay, so now here you can see that this is with reference to plane 0, 60, 90, then 120, 150, and 180. And you can see that how the turbulence is changing when you are moving from plane alpha is equal to 0 degree to 180 degree. Okay. So now these are the some contours which has been drawn on the basis of the what we have collected through our experiments. So we have collected with our experiments the U component, V component, W component, then also U prime, this component of the velocity, then this also we have collected the data. So these all components were basically collected through acoustic Doppler velocity meter along the or around the Scava hole or in the vicinity of the bridge pier. And now you can see that these some plots have been drawn in order to get more understanding of the flow pattern, what is happening here. So here you can see that this is basically with reference to the alpha degree plane, which is just up. This is in the just ahead of the pier, that is alpha is equal to 0 degree, means upstream of the pier. And this is basically the Scava hole geometry, and this is what we have at 400 millimeter, that is 40 centimeter. So this basically all area is related to the Scava area. And in this you can see we have the normalized profile of the mean velocity. So this mean velocity is basically different with the velocity, this U, V, and W. So this mean velocity has been taken with the square of all these velocity. Okay, so that is what we have the mean velocity. So that is what we have tried to draw the contours, where we are getting the more magnitude of the velocity. So here you can see that within the Scava hole, these are the contours which are showing the values from 0.2, 0.6, 0.8, where and you can see that here above the Scava hole we have almost the same velocity of the flow. If you go with the kinetic energy contours, then what we say that the turbulence here, you can see that here we have the velocity of, we have the value of this normalized value is K divided by U star square. So this normalized value, you can see that magnitude is 14 within the Scava hole. Okay, so this is showing the turbulence intensity here, while above here you get the less values. Similarly, we have also drawn the sketch for the normalized component of the turbulent density as 0-degree plane to give more insight in this area. And you can see that this contours are showing within this area and showing the intensity is here more when we compare this above area. Now these are the Reynolds stress component here. So try to sketch and identify. So now go with this 180-degree plane just downstream of the plane. So here you can see this is the Scava depth here. And this is the depth total. Depth of Scava on the downstream side. And this is what we have. Component of the mean velocities here. So moreover, as you are moving away from the flow, this component is increasing. That means we are diminishing the effect of this pier on the downstream side as we are moving away from the pier. So this is the basically normalized value, means 0.9 means you are just approaching towards the approach flow velocity, that is 28 centimeter per second. Okay. Now here this is the kinetic energy parameters, and here you can see that this is more intensive contours having the magnitude around 80 and so on. As you are moving away, these contours are getting less magnitude. And also when you compare it with the 0-degree, then also you can see that the area or the wake region is more turbulent when we compare with the upstream area. So now this is again the Reynolds stresses which has been computed also, and the normalized. Just wait. This is not Reynolds stresses. This is the turbulence characteristics. Okay, for the U component, V component, and the W component. Also, you can see there here W component is showing the more magnitude here, and these are the Reynolds stresses. And also you can see that Reynolds stresses values having the more magnitude when we compare with the 0-degree plane. So that is what we have done here regarding the flow characteristics and the flow parameters. So next coming slides show the comparative study of the flow field. As I discussed you that we have taken the flow field measurement around the 4 different pier geometries. So here this following 4 or 5 slides explain the comparative study of the flow field parameters here. So this is what is we have done here. We are making a comparison of the individual components. So this slide is basically showing the U component of the velocity, and here you can see that this is basically the notation chart here we are using. So we are here having the 4 different pier geometries, okay, with the different location of the piers. So y is equal to 0 means at the river bed, footing is above the river bed, and this is footing is below the river bed, and this is footing below the bed. So this is below bed, this is above bed, and this is what we have y is equal to 0 at the bed. Okay, and this is for the uniform pier here. So here you can see that in all cases, if you go with this, the U component of the velocity and this all chart are basically for fixed location. That is, for example, at r is equal to 100 radial distance from the pier, then 140, then 1 centimeter, and how the velocity U component is varies with these all footing locations and all these pier geometries. Just wait. So here what we have, if you see that close to the pier, as we are discussing with r is equal to 0, and in the upper region, These profiles of U component velocity show almost similar trends. Okay, no change, no behavior. But within the Scava hole, what we see that within the Scava hole region, for experimental run, this number 3, that is NUPSS3, that is what we have. The U component is here very small, up to this only. While this uniform pair Scava hole, what is happening here? We are getting this U component of the velocity. And why it is happening? Because for all others, the we are having the top of the footing. Okay, so for all other, what is happening here? For all other combination, which is this combination, the first reading is just lying on the top of the footing. That's why we are not getting this. We are not getting the result for all these things. So here, for rest other, as you move away, you can get these values for all these pair geometries. And here you can see that this is the negative values, which means there is a reversal of flow. Here also we are getting reversal of flow. And as you are moving away, we have taken up to here 300 millimeter, which is coming into the Scava hole. So here what we are getting, as we are moving away from the Scava hole, the negative or reversal of flow getting decreased. Now similarly, we have not taken here the V component, as we are not getting significant change in the value of V component, while this W component is more significant, as that is basically contributing towards the vortex formation. So again, as I told you that when you discuss with this R is equal to 100 meter, then always we are getting this value of W component only for the uniform pair Scava hole. While if you are at this position at R is equal to 140, then we are all having what we are having here. You can see that we have compared all these data for all these 4 cases, and the maximum value of the W component. Okay, this is what? This is the negative value, means we have the upward motion of the W component of flow, and here we have the negative value, that means W. So here the magnitude with reference to this condition is more when we compare with all other 3 values. And as the flow, we see that as we are moving away from the pair, the W component diminishes, that the effect of pair and Scava hole geometry diminishes. Now these are the again representation of the same data in the form of so these 3 pictures are clubs here for U component and the W component. So these are the figures same. Okay, so need not to describe again, and that has been taken from the publication. Again, here we have shown the comparison of the U component of the turbulence intensity at the plane of alpha is equal to 0 degree. Okay, so again, the turbulence is our top of the footing is exposed. So here this is the values. So this is the V component here, and this is similarly for the W component. So these are all the turbulence component for all these 4 cases, and comparison has been made. And similarly, this is at the 180 degree plane. Okay, so when we are having this wake region downstream, and here you can see that we are getting the different result when we compare it with the results of the upstream of the plane. So that is what we are having here. So here you can see that this is again at the for the uniform pair values. So behind the pier, if you see this value, this is for the uniform pier Scava hole. Again, here for all others, we are not observing this value here in the Scava hole area, in the wake region. Why? Because we are having the top of the footing for all these values. So Scava did not Scava hole did not allow to develop in that area. So now if you go beyond away from the this is the pier, okay, and if this is the approach flow, this is the downflow here, and this is what we have, like this type of Scava hole, for example. Okay, so this is the at r is equal to 100. Now this is the plane which is related to r is equal to 140. So when we are using the data and when we are capturing the data for the uniform pier, only this pier, then in that case we are not having this footing. So we are getting the result up to down, as this is the case. Why? When we are working with r is equal to 140, we are able to get the data for all the pier configurations. And here you can see that there is a difference here. You can see that this is for the uniform pair. We are having the U positive values for the case of uniform pair. But in case of the non-uniform pair, again, we are getting the U negative value. That means when top of the footing is above the river bed, then also behind the pier, we are getting the reversal of the flow. As the flow passes away from this Scava hole geometry and away this pier, then what we are observing that we are getting the all positive values. This is almost out of the Scava hole. And what is the trend? That as you are moving towards the water surface, the velocity component, that U component, is decreasing towards the water surface. As at the top of the water surface, we are getting the more turbulence. Now coming to the next, that is the W component here. And if you compare again the W component, so what you can see that below this, we are having these all are the below the or within the Scava hole. Okay, and this is away from the pier at a distance of r is equal to 350. Here what are you getting? Hello. So here you can see that W component is here. What is the value here? W component is here positive here. And what positive value of W indicate that W is positive? Then we have the upward the W is, that means motion is in the upward direction. So here in all cases we are getting the positive values here. And also you can see that in all cases when footing is exposed, we are getting the higher magnitude of the component of the W. Either it is W or either it is V. Now this is again representation of these two figures, and only selected figures has been taken in this, only for this U component. Now this is the fluctuations, comparison of the fluctuations in four cases. So you can see that no conclusive trends we got from this. Almost if you see that for this, when our footing is exposed, we are getting the more turbulence in all the cases. While we vary, we are capturing the distance at different radial distances. Now this is for the V component here we are having. Again, you can see that at the 180-degree plane, there is a fluctuation or intensity is a little bit more when we compare it with the U component. Here the magnitude is varying from scale 0 to 8. Here what we are having, the magnitude is varying from 0 to 18, which shows that how V component is having fluctuations in magnitude. Also, this is the W component here also we are having, and you can see that what are the trends we are having in the flow structure. So now coming to end of this flow structures we have discussed. So now something little about the computational flow dynamics. So this is the what results we have taken here. That is the experimental results, but as we go with the literature, then what we see that simulation of flow structures in the Scava all-around peer is also reported by several researchers, and the name is indicated here, and most of them has used the Reynolds average Navier-Stokes models, that is known as RANS. So computational fluid dynamics, if we talk about this, the present ability to simulate erosion and scour at pier is limited, and thus hampering its practicality of this cover depth estimation. However, some attempt has been made, and in some cases we get the good results, but still there is a scope to work in the field of the computational fluid dynamics. So here, these are the references for the future readings, and so you may go through that. So that all are the references which you can refer if you want to go or do some more research in that area. And with these words, thanks to all of you for the patience listening and the questions in between the presentations. And I also welcome the questions if any have regarding the or any queries. Although I have taken a little bit more time.
Sir.
Yes.
Good afternoon, sir.
Good afternoon.
Sir, there's a reference that you have mentioned, Bruisers and Rurki. The book name is Scouring from Alchemy publication.
Yes.
Sir, I have tried finding that book if it is available online. But is that book available online in PDF format, sir?
That book is, I think that is available online. You can purchase it online, or otherwise you can visit library in the Department of Civil Engineering at IIT Rurki. We are having one such copy, and I referred that copy.
Okay, sir.
Okay, I don't have this copy.
Yes, sir. Because I tried to find that book, but it is not available with our library, and library that are basically approachable to me. But I was thinking that book might be available with IIT for sure.
That is available at Department of Civil Engineering library. Okay, you can go there and you can refer that book. That is a good book. That is a good manual. Okay, and also
a lot of referred that book.
And also you can, if you want to go online, then you can also refer this HEC 18 circular. That is also good for reading. Okay, that's a very good manual.
HEC 18 peer scour, sir.
Yes, sir. Okay, that is a very good manual. Give a good insight about that area.
Okay, sir. Yes, it is. And the PDF is also available, sir.
Yeah, PDF is also available, so you can refer that. So that is a good manual, and yes, I am also going through that.
Okay, for sure. Thank you very much, sir.
Welcome.
Yes, sir.
Hello, sir.
Hello.
So is there any question so you can ask?
Yes, sir. Sir.
Yes.
Sir, what is the most suitable type of bridge in hilly areas?
In the hilly areas, basically, you may provide RCC bridge also. Basically, normally what we Indian subcontinent, as I told you, that we normally prefer with the circular pier geometries.
In terms of cantilever bridge or suspension bridge, like because I think in cantilever bridge there is no problem of providing piers as in more numbers. So
that is also depending upon what is the width of the waterways which you want for which you want to create a bridge. For the shorter,
okay,
obviously there will be no need to create a pier in between. Okay.
Okay.
Normally in the hilly areas, what we are doing, we are providing the steel bridges, steel trusses bridges. If you are having the shorter span.
Okay, sir. Okay. Thank you, sir. Thank you.
Okay, welcome.
So thank you so much, sir, for delivering such a wonderful lecture on this topic of flow behavior in scour around piers. So on behalf of Civil Engineering Department, we are thankful to you for this lecture. And tomorrow also we are going to listen you on the title Vector Analysis of Flow Pattern during scour around the pier. So thank you so much, sir. I hope all the participants have learned a lot from this lecture, and tomorrow again we will listen more on this topic. So thank you so much.
Thank you, Professor Saab. I am also enlightened that you have given me opportunity at this platform, and in future also, if you have and also I want to say to all the listeners and all the participants, in future also, if we have some doubts, if we have some queries, then they can contact with me. I'm always here.
Definitely, sir. We will keep in touch.
As I can do. Thank you. Thank you.
Yes, sir. Thank you so much, sir.
Should I leave?
Yes, yes, sir.
Okay, okay, thank you.
Yes. So all the participants, now we are having the third session, so we will meet again within 15 minutes, or you will have a 10 to 15 minutes break only. So we will start at 3:45 for the next session, third session, on measurement and quantification of flow turbulence in mobile bed channel by Dr. P.L. Patel, sir. Okay, so we will start the lecture sharp 3:45. So be on time.
Can we leave, sir? Can we leave?
Yes, if you wish, you can leave, but you join at sharp 3 by 3:45.
Okay, sir.
Okay, sir.